So now we will try to expand the scope of differentiation techniques further to now products of two functions. Okay, so you may have seen how to differentiate x squared and how to differentiate e to the power of x, and if you know that, you could differentiate an addition or subtraction of these two separately, but right now you may not know how to differentiate it if they are multiplied together. Okay, and I can tell you that the answer would not just be this. Okay, it is indeed more complicated than that. So we have products of two functions in all three of these examples, as you can see, and I will give you the derivatives, and you can pause and try and work out what the rule might be based on these three examples. And I think you might be able to spot it. So the derivative of x squared times e to the power of x is 2x times e to the power of x plus x squared times e to the power of x, which I could factor into something that is a bit more manageable, but that's fine for now. So x times sine of x, the derivative would be sine of x plus x cos of x. X times cos of x. And our final one would be minus 3x squared ln of x plus 4 minus x cubed over x. Okay, so you may want to pause it now and see if you can spot what has happened here in each one of these. Clearly I have sort of two different terms, big terms added together, but what's happening on each one of them? Where might 2x come from? Where might cos of x come from? How have we got this over x thing here? So pause it now, have a think about it. Okay, so maybe what you've noticed here, okay, if we call this, no, let's call this, f and g, okay, f of x and g of x. What you see here is that I have the derivative of f times the original g plus the original f times the derivative of g, even though that may not have been clear which one was which for e to the power of x, obviously. Here, well, it seems as if I just have g, if I've got a new f and g, that is. And so, is that different? Well, the derivative of f, of course, would actually just be 1. Okay, so I could think of this as 1 times sine of x, and then this is the original f, and that's being multiplied by the derivative of g, cos of x. And the exact same thing is happening in this third one. I have the derivative of f, which would be minus 3x squared times g, plus, well, this one's a little bit more tricky. I have my original f quite clearly. Now the derivative of g would be 1 over x, so 4 minus x cubed times 1 over x can be written as this fraction, which is what I have. So it looks like I have the same thing going on in all three of these examples, so that is indeed my rule. Okay, if I have to differentiate f of x times g of x, okay, two functions multiplied together, my rule will be the derivative of f times g plus the original f times the derivative of g. You could do these the other way around as well. Obviously, addition, you can switch the order, and in the formula booklet, it's a well, it's easy enough to follow. U and V are both functions of x. Okay, so you have, well, they have the opposite order in this one actually. You have the original u times the derivative of v. Okay, you could maybe write it like this if you wanted. And then you have the original v times the derivative of u. Okay, so yes, you could also switch the order within each term as well, which is obviously still fine. So a fairly simple rule, I think you'd agree. So a couple of examples. If I was going to differentiate 2x times e to the power of x, I can label this f and g, and maybe I don't need to do it for this one, but a really good habit is writing it out in full with your 4 things that you're going to need. Okay, fg, derivative of f, derivative of g. Okay, just to gather your thoughts, and the next rule that you'll learn, this kind of technique might be even more useful. Okay, with a more complicated rule. So then you can think about your rule. Okay, I'm going to do this times this, and this times this. So which one should I do first? Okay, let's keep it in this order that I wrote before. So I'll have 2 times e to the power of x plus 2x times e to the power of x. Again, e to the power of x stays the same, which might confuse things ever so slightly for this rule. Okay, and we are going to call this the product rule, if that wasn't clear. And I've just factored it, that wasn't particularly necessary. And a little bit more tricky here. Okay, why don't I call it u and v this time, just to mix things up. Okay, there's no reason why I have to call it f and g. There's no reason why I have to call it anything at all. 5 ln of x would, the derivative would be 5 over x, and if I call my v sine of x, then v dash would be cos of x. Okay, and those are my 4 things I need to use, and dy by dx, the derivative, would be, why don't we do this order for this one? 5 ln of x times cos of x, and then v times du by dx, v times u dash. Sine of x times 5 over x, I might just combine that into one slightly neater fraction, and I am done. That is the derivative. Okay, a sort of long, complicated function, but that is the correct derivative. Okay, and let's not lose sight of what we're doing here. These are derivatives. These are functions for finding the slope of a tangent at a certain point. Okay, so if I wanted to find the slope of this curve at x equals 2, for example, okay, this is the derivative. I would then plug in 2 into x, into all 4 of these places, and I'd get a numerical answer that would be the slope of the tangent at that point. Okay, I could find equations of tangents and normals. I could find stationary points, inflection points if they have them. Okay, I could find the second derivative to classify stationary points or find inflection points, or looking at the concavity. All of those things are now possible with a product of 2 functions, and that is through the product rule.